Hello and welcome to the Chapter 1 podcast on Section 4. So today we're going to talk about units of measurement. So the units of measure that are agreed upon by international scientists are the SI units of measure. It's like SI is short for System Internationale or something like that. These are agreed upon by the world. These are standard measurements. And for the most part we'll be using most of these measurements. Some we won't be using so much. Others we might be. For mass, the name of the unit is the kilogram, and the abbreviation is kg. We're going to probably use gram because we're not going to be using such large amounts, typically in experiments and things. Length is a meter, something you're probably familiar with from math and from other science courses. Time is going to be in seconds. Temperature is kelvins. This is an absolute temperature scale, which we'll talk more about. For the amount of a substance, that'll be a mole. I know some of you know what moles are and others of you don't, but we will go over what it is in due time. For current, we do amperes. Some of you guys might have heard them called amps for short. And then for luminous intensities, we use candelas. And then the corresponding abbreviations here are on this figure. You're also going to need to be familiar with metric prefixes. One of the reasons why we use the SI units of measure in science is that it's based upon units of 10. So going up or down is just by adding, by either multiplying by 10 or dividing by 10. This is different from English measures. Like for instance, if you want to go from inches to feet, you have to remember that there are 12 inches in a foot. You have to remember 3 feet in a yard. You have to remember 5280 feet in a mile. Those are all like very difficult conversion numbers to memorize, whereas with the metrics we just need to move the tens place over one way or the other. What you see here on this figure on the bottom are some of the abbreviations that will be used throughout the book, and these are abbreviations we can throw of any unit of measure. So in this example they're using meters, but we could also throw it in front of seconds if we were doing time, or moles and grams and things like that as well. And we'll practice this in class as well in terms of converting from one unit of measure to another one. Oops. In terms of temperature, this just measures how much heat or how hot or cold something is. The old SI unit used to be the Celsius scale. This is a relative measure of temperature based upon water's boiling point and freezing point. So they just arbitrarily made the freezing point of water 0 degrees Celsius and the boiling point 100 degrees Celsius, and they kind of moved from there. Now with the Celsius scale and also with Fahrenheit, you can get negative numbers. With kelvins, you'll never get negative numbers. This is what we call an absolute scale, which is kind of close to a measure of the degree of kinetic energy something has. It's not a direct measure, but it gives us some insight in terms of how much kinetic energy something may or may not have. It's a contributing factor. So to convert from Kelvin, from degrees Celsius to kelvins, we add 273. Now there's a reason why it's 273, and when we discuss gas laws and such a little bit later, it'll become more apparent why. And then we also have the Fahrenheit scale. This is the one we use in the United States. So when you watch the weather report on the news, this is the one that's typically used. And you can see we can either go from Fahrenheit to Celsius or Celsius to Fahrenheit. You can see that the conversion isn't easy to remember. Okay, but these are things you're going to have to know. In terms of derived units, basically we can use SI units to come up with other quantities. So for instance, rate of speed is a derived unit, so it's meters divided by seconds. So derived SI units have 2 or more units of measure associated with it. Volume is another example. We have cubic centimeters. Milliliters are also used for volume, so these are actually one and the same. For water, 1 cubic centimeter equals 1 milliliter. Typically, things that measure volumes either in cc's or milliliters are things like syringes, things they use to give shots with burettes, which you see here in this example, on this figure here on the right. Graduated cylinders, and then also used for other things as well that we might see throughout the course. So pipettes and volumetric flasks. Density is another derived unit. It's mass divided by volume. It can be expressed either in grams per cubic centimeter or grams per milliliter. Sometimes you'll see other units of volume like liters, for instance. Densities are temperature dependent. This is because the volume of the liquid will vary slightly as the temperature changes. And weight and density are not the same thing. Okay, and then here's some general densities of some substances here. Typically, with densities, if something is less dense than something else, the less dense thing will tend to float above. Here we have a sample problem. Here we're calculating the density of a 374.5 gram sample of copper if it has a volume of 41.8 cubic centimeters. The equation for density is mass divided by volume. And so we have our mass, which is indicated by the grams, and our volume has the cubic centimeters. So using the units of measure allows us to kind of put things into the equation properly. D is for density, M is mass, V is volume. And then we put in our numbers, and the answer ends up being 8.96 grams per cubic centimeter. We can also do another kind of density problem where we're solving for volume instead of density. So in this example, we have 15 grams of ethanol. The density is 0.789 grams per milliliter. So what's the volume, or how many milliliters do we have? We can go ahead and use our same density equation here. We have our density, and we substitute in our mass, and we solve for V, which is our volume. We do our division, and we end up with 19 roughly milliliters for our volume. And in our last problem, I can give you the density and I can give you the volume, and we can solve for mass. So again, we're going to use our density equation. We substitute in our values. I know that this is volume because the units is milliliters. The density has 2 units. And then we solve for mass, and we end up with 340 grams. There's a reason why I wrote the number like this, and when we talk a little bit about more about measurement in future sections, it'll make more sense. So I will see you later.